Ladies and gentlemen, welcome to lecture 23. In this lecture, we will start with something new. We will start with chapter number 5. In this chapter, we will be talking about integration, about Riemann integrals. In fact, we will see what this integral is all about. You will see how or I would say why this integral is so important. Basically, it will allow you to compute the area under the graph of a curve. So that's the important role of the integral. But not just that. So in this chapter, we will learn how to compute, more or less in this lecture, how to compute the antiderivatives of functions. Then you will see that we will deal with Riemann sums. You'll see how to approximate these integrals by a sum. And then we will see some other techniques in computing integrals. Here it will be very important for you to know the antiderivatives of elementary functions. But we will take care of that in this lecture. And also, you will see, like I said, towards the end of this chapter and of course, of this course, other techniques of computing undefinite and definite integrals. I don't know, substitutions and so on. And towards the very end of the course, we will be talking about some more qualitative properties of the integral, such as the mean value theorem, but this time it will be for integrals. And last but not least, I think this is the very last lecture. Usually this is not covered in any Calculus 1 courses, but here at Tech it looks like it's covered. We will be talking about approximation formulas, about integration formulas, how to approximate an integral, because you will see examples of functions that whose antiderivatives cannot be expressed in terms of elementary functions. So in this case, we need to approximate those integrals. So this is where the approximation formulas or quadrature formulas, whatever you want to call them, come into play. All right, so that would be the summary for this chapter. In this lecture, I will start with anti-differentiation. All right. In fact, let me tell you something before I dive into the subject. Let me tell you something about my cool picture. As you can see, this is my hometown of Constanța in Romania. And we used to go to the beach. So if you see right here in this gulf here, we used to go to the beach, and my high school was right here, somewhere here. So every time we used to go, we finished, well, even if we skipped some classes, we used to go to the beach. So that was fun. Anyway, so let's get started. Like I said, I will start with antiderivatives, with something very basic for you to know. And like I said, this is a must for you. So the title for this lecture is will be called Antiderivatives. By the way, I hope I will not lose my voice at some point if I'm screaming around here. Hopefully this doesn't happen. All right, so first we would like to see what is anti-differentiation all about, right? So let's dive in directly and see exactly what do we mean by anti-differentiation. Well, as you can imagine, there must be some kind of a way. So if we have a function, we can take the derivative of that function f, and we can write f prime of x, right? But also, there should be another procedure that will allow me to go back from the derivative to my function f, right? And from f to f prime, I will take the derivative. But now if I want to go back from f prime to f, maybe I will take the antiderivative. In other words, a function of capital F, right, is called an antiderivative of a function f, and let's just say f is defined on an interval I, doesn't matter, closed, open, if this relation will happen. So if the derivative of capital F of x is nothing else than just f of x for all values of x in that interval, right? So that is the thing that you need to know. You see, this is the relation, the very important relation. So that's how we will define the antiderivative of a function f. Again, you have the function, and you would like to see the derivative of what function will give you this, your function. So that's what we will call, this is what we call the antiderivative. Okay, so let's see an example. So let's take the function f of x equals 2x. Of course, clearly, you know that there exists another function whose derivative will give you 2x. And that other function that satisfies this property is nothing else than just capital F of x equals x squared, right? Because if you take, just look at the definition. If you take the derivative of f of capital F of x, right? So the derivative of x squared is nothing else than just 2x, right? So you can say x squared prime is 2x. Great. But now the question is the antiderivative unique? You see, because I can also consider, so you see, this is the this is an antiderivative of f. Because it has this property that that capital F prime of x is f of x. Well, great. But what if I consider capital G of x to be equal with x squared plus 3? Well, guess what? If you take the derivative of x squared plus 3, right, x squared plus 3 prime, this also gives you 2x. Wow. So you see, I took two different functions, capital F of x and capital G of x, look at them here, and whose both derivatives will give me f of x. So what can we say about the antiderivative? Is it unique? How many of them are they? What do you think? Exactly, there are infinitely many of them, but is there a, exactly, so because that constancy can be anything, but no matter how many of them are there, all of them will differ by a constant. So that's what you need to know about the antiderivative of a function. So you see here, the general form of an antiderivative of x is capital F of x plus c. So all of them will differ by a constant. So that's what you need to know. And this is very important. And you will see that we will write this in a certain way. right? And so we will have the following notation. And let me explain this. As you can see here, I will write this in the following. So the integral, you see this S sign or whatever dollar sign, this is how we will denote the integral. So let me write it here. So this is the integral. And we're going to read this as following. The integral of f of x dx is capital F of x plus constant plus c. And that c is a constant. Well, let's see what are these things here. So as you can see, that S sign or dollar sign, whatever you want to call it, is what we say is the integral. Then the function inside the integral we'll call integrand. So dx will be the variable of integration, and we're only going to stick to dx because we don't want to deal with some other type of integral. So we're going to stick to to Riemann integrals. And capital F of x is the antiderivative, right? And c is the constant of integration. In other words, we will write it in this way. So the integral of f of x dx is f of x, so capital F of x plus c. And like I said, the integral of f of x dx is called the indefinite integral of f. Or you can actually read it as the indefinite integral of f with respect to x. So that's the notation we're going to use. And in fact, I would like to go back to the previous slide. What can you tell me here? I mean, based on what we, so what did we see? So let's write this. So example here, let me give you a quick example. What can you tell me about this? So the integral, and look here, I would like to go back of, so f of x, okay, let me take f of x to be 2x, just like in the previous, f of x equals 2x. And what did we say? We say that, so we saw that this function g of x, which is x squared plus c, is the antiderivative So this is the antiderivative of f. So in our notation, we can write this. So we can write in the following way. So we can write that this integral of 2x dx, right? As you can see here, f of x is 2x, right? So this will be what? Will be, well, now x plus c. C constant. So this is how you can write this. So you can express, instead of me writing this is the antiderivative of this, that is the antiderivative of that, I'm just going to write in a very simple way, like this. So the integral of 2x dx is x squared plus c. In other words, the antiderivative of 2x is x squared plus c, right? Okay. All right. So again, look at this. This will be the notation that we're going to use, right? So this will be the integral. Once again, this will be the antiderivative notation. Like I said, the integral of f of x dx is capital F of x plus c. So it's antiderivative plus a constant. All right. So make sure you're gonna towards the course of this chapter, you will have to get used to this notation, this new notation, right? This dollar sign, whatever. It doesn't look like a dollar, but anyway. So this is what you have to get used to here. This notation. All right, great. Now let's see some properties and some examples. And I would like to see what kind of, well, since we introduced this new operation, this new integral, we would like to see, well, this integral, we'd like to see how we can operate with this integral. So we'd like to see what kind of rules does this integral satisfy. And you'll see that this integral will not, it will behave nicely, but not as, it won't be as nice as you want. So it will be additive, so you can add two integrals. This basically the sum of the integrals will be the integral of the sum. But unfortunately, the product won't behave in the same way. Anyway, I'll make myself even clearer once I point out the main properties of the integral. All right, great. So let's see what are the procedural rules for this integral. And well, the first property that you need to take into account is the following. Look at it. So you see you have a constant. So let's just say this is 1, this is 2, this is 3, this is 4. So you have a constant. So if you multiply the function by a constant and then you will you integrate that, right? So in other words, the integral of c times f of u du, you're going to take the constant out, right? So you'll take the constant out. So this will be the constant, the c times the integral of f of u du. So you don't want to deal with the constants. We're just going to take them out, and then you'll compute the integral. So that's the first property. In fact, let me draw a line here because I'd like to make an observation. The second property is that, well, this is actually very nice. So the second property says that you don't have any problems when you add up functions and then you integrate them, because the integral of the sum is the sum of the integrals. In other words, the integral of f of u plus g of u du, everything du, is the integral of f of u du plus the integral of g of u du. So it doesn't matter how you add or how you integrate. So if you add the functions first, or you want to separate them to add to compute each integral and then to add them, is the same thing. And yes, yeah, you can say the constant rule for integrals. So somebody asked, Eric asked, do these rules have names like for the derivatives? Yes, the constant integral rule if you want. So this is the additive rule, or the sum rule if you want. Let me put it like this. And this one here will be called the difference rule. But you don't have to remember them by heart. I mean, they come as natural as possible. And well, okay, 3, but you can see, well, if something works for the sum, it should also work for the difference, right? Because the difference is nothing else than just the sum. When you say f of u minus g of u is nothing else than just f of u plus negative g of u, so it's the same thing. In other words, the difference, the integral of the difference of two functions is the difference of the integrals. In other words, the integral of f of u minus g of u du is the integral of f of u du minus the integral of g of u du. So that's the difference rule. But all these three rules combined, we can write them in one certain way. Let me put it here. Let's say the fourth rule, which is nothing else than just 1 plus 2 plus 3. So a combination of the first three can be expressed like this. So this is what we call for our integral to is called bilinear. In other words, as you can see there, you have if you have a constant multiplied by f, and then you have another constant. And here, let me just say that a and b are constants. This is important. Real constants. So if you have a constant a multiplied and you multiply it by f, then you have another constant b and you multiply it by g, and you add them, you subtract them, it doesn't matter, and you take the integral of this mess, it will behave very nice. So we get the constant, you will take out the constant. Then for both f and g, and then you're just going to add or subtract the two integrals multiplied by the constants. So in other words, the integral of a f of u plus minus b times g of u du is a times the integral of f of u du plus minus b times the integral of g of u du, right? So all the first three combined will give you the fourth one. So if you remember the fourth one, I think it's enough. And of course, you can take the constants to be a equals b equals 1. You will get the second rule, or the third rule, sorry. Well, the second and the third depends on how you take the plus or minus. Also, if you take g to be 0, you'll get the first rule. So all three of them combined in one, it's the fourth one. So that's what you need to know. The integral is bilinear. That's what we call. So the integral is bilinear. So that's the word. Okay. All right. So now let's see some formulas, and we would like to see more examples on how to. So once we know these rules, we have these rules in mind. Now there is a way for us to compute some antiderivatives of functions. Well, let's do that. And let me start with the easy example first. Look at this one. Look at this baby right here. See it? So it's the antiderivative, so it's the integral of u to the power n du. In other words, our function here, let me just point this out. Let me write. So in this case, f of u is u to the power n, so it's the power function, right? We know how to compute the derivative of this guy. But now we also want to compute the antiderivative of this guy. In other words, we would like to see what is the integral of u to the power n du. Well, can you think of a function whose antiderivative, whose derivative will give you u to the power n? Well, u to the power n plus 1 over n plus 1, right? Because let's compute the derivative. So d over du, let's say, of u to the power n plus 1. Okay, let me write it this way. Over n plus 1. Well, guess what? This can be written as d over du of 1 over n plus 1, right, times u to the power n plus 1. But this is a constant here, right? So this is a constant, so we will take out the constant, as we have seen from derivatives, and I hope you all know this. And this would be 1 over n plus 1 times d over du of u to the power n plus 1. But the derivative of this guy here, as we know from the derivative rules, is nothing else than just n plus 1 times u to the power n plus 1 minus 1, which is u to the power n. Well, voila, you're going to simplify, we're going to cancel n plus 1 there, and then you'll get exactly u to the power n. And now if we reverse this operation, we can say that the antiderivative of u to the power n is, so let me just write here, all this mess here, this guy here is u to the power n, right? So look, we started from the derivative of u to the power n plus 1 over n plus 1, and we ended up with u to the power n. All right, great. And now I'm going to reverse the operation, and I'm going to say that the antiderivative of u to the power n is u to the power n plus 1 over n plus 1. Well, not just like that. It's one of them. You need to take that constant plus that constant, right? So see, we have this. So to express this in a best way possible, we can do it like this. We can write this in terms of our notation. We can write it in this way. So we will write this as the integral of u to the power n du as u to the power n plus 1 over n plus 1, right? Plus that constant c, whatever, there are infinitely many, so you can put plus 2, plus negative 100, plus 10 billion, whatever you want to do. And this happens for n different than negative 1, because there will be a special case, right? So this is the rule. For example, what if we have to compute, okay, let me give you a quick example. Look at this guy here. So this is the example for n equals 5, right? So, like I said, I'm stressing this guy here to be different than negative 1. It's important. Because we will see what happens afterwards. All right, so now let's see an example for n equals 5. So we would like to compute the integral of x to the power of 5 dx. Well, beautiful. It's in front of you. You have the formula. So the integral of x to the power x to the 5th is nothing else than just x to the 5th plus 1 over 5 plus 1 plus c. Well, which is nothing else than just x to the power 6th over 6 plus the constant c. In other words, you can say that the antiderivative of x to the 5th is x to the 6th over 6 plus c. Pay attention. You see, antiderivative and derivative are two different things. So the derivative of x to the 5th will be 5x to the 4th, but the antiderivative of x to the 5th will be x to the 6th over 6 plus c. They are two different things. Right? So this guy here is the antiderivative of this guy here. So this is the antiderivative of x to the fifth. So that's what you need to know. All right, and now I told you that we would like to exclude the case when n is -1 because that will be a special situation, and I would like to address that right now. So look at this. In other words, what happens when when n is -1? Well, it's not as you would expect to be some kind of a power function multiplied by some constant. So in this case, we will have to deal with the logarithm. Look here. So the integral of u to the power -1 du, and of course you can write u to the -1 as 1 over u du, right? So you can do that. And once you do this, this will be nothing. You will have to look for the antiderivative of 1 over u, which is probably you have noticed by now, I hope, it's nothing else than just ln of the absolute value of u plus c. So that's what you need to know. This is, like I said, let's say another rule of computing antiderivatives. Right? So pay attention, look at them, look at both of them. You will see that they're quite different. Because of course, well, depends on how you define. If u is positive, then you can take ln of u, no problem. So remember that ln of u prime is 1 over u, right? Remember that? So in other words, you can say that this guy here, right? This guy here, this is the antiderivative of 1 over u. Keep that in mind. All right. So these are the two rules, the first two rules, but also we would like to see something that looks nice. And let me tell you another one. Look here. The integral of e to the power u du. Well, there is also this function that doesn't, when you integrate it, when you differentiate it, doesn't change, and that is the exponential function. So when you have, it will stay the same basically. So the integral of e to the power u du is e to the power u plus c. Right. By the way, I don't want you to get confused here. E to the power u is the variable. F of u is e to the power u. U is not like a function u of x. So I'd like to stress this out. Right. So in the first example, I used x. In the second example, I used u. So u is not u of x. We'll get there at some point. We will talk about the u substitution. You will see the difference between them, just like you have seen in the when we computed derivatives of composite functions, right? And we use the chain rule. So there will be something, well, sort of similar here for integrals. All right. So these are the three rules. I would like you to stare at them, like have a really close look at these three rules, because we would like to use these in some examples, and you will have plenty of integrals to compute, especially in your homework. All right. So these are the first three rules. We will see some others through the course of this class. All right. Now let's see some examples. The first one, look. In fact, I would like to give it, anyway, look at this one here. So the first example that I have in mind is the following. In other words, in fact, you know, I haven't written details there, so maybe you can justify the details for me. So, in other words, we say that if we'd like to compute, and maybe I should write it in this way, so the integral of x squared plus 4x cubed dx. You see, the antiderivative of this is given by this guy here. But now the question is why? How did we get to that? I want you to tell me. So think about it. So what should we do here? Well, let's see. Exactly. So exactly, Eric, correct. So maybe we should use the sum rule first. So this would be the integral of x squared dx plus the integral of 4x cubed dx. And then what? What to do next? So what is the, we can we compute the first integral? Can we express the first integral based on what we know so far? You see, is there a rule that will allow us to do that? You see it here? Look at it. It's the first one, right? So in our case, the integral of x squared will give us what? Can you tell me? Will be what? Will be x cubed over 3 plus, let's say, some constant c1. Great. So this will be the first integral. So let me put it like this. Right? And now let's see the second one. For the second one, we can take the constant out, right? Plus 4 times the integral of x cubed dx, right? So we apply the constant rule, and this will give us, so let's keep the first one, x cubed over 3 plus c1 plus 4 times the integral of x cubed is nothing else than just x to the 4th over 4. And let me put plus c2, let's say. And now we're going to multiply everything together here. X cubed over 3 plus c1 plus 4 and 4 will cancel, plus x to the 4th plus 4 times c2. But I don't care. I can write c1 plus 4 times c2 as another constant c, so I don't care. So there you go. So this guy here will be this guy here. Right? Does it make sense? So this guy, so here is this one here. So the only thing we used we used the first sum rule, and then we used the constant rule, and we just computed the integral by using the first one, the integral of the power function. All right, great. Any questions about this example here? Is it clear to everybody? Let's see another question. Because look here, Eric. just algebra. It won't cancel. You'll write. Look, you have here. You see 1 plus 4c2. You'll write it as a c, and that's it. Instead of dealing with 10,000 constants, you just write one of them, and that's it. Does it make sense now? All right. Let's see, any other questions? Don't feel free to ask me questions. Like I said, it's good for you. All right. If there are no other questions, let me show you another one. Look at this. This is so this was the first one. This is the second example. So we have the integral of 3 over x is nothing else than just 3 times the natural log of the absolute value of x plus a constant c. And why is that? Can you explain this to me? Why is this true? N equals -1, correct. So we have this rule here, you see? Exactly. So the integral of 1 over u is ln of the absolute value of u plus constant c. So in our case, we're just going to take the 3 out. So we apply the constant rule. So let me write it here. So in details. So the integral of 3 over x dx is nothing else than just 3 times the integral of 1 over x dx. And this will be 3 times ln of absolute value of x plus a constant c. Okay, this was an easy one. But now let's see another one. Look at this guy here, the third one. Well, you see, when we would like to compute the integral of the radical, so we should be a bit careful here. So I would like to compute the integral of this function, 5 times the square root of x dx. Well, no problem. We said that the square root of x can also be written as x to the power 1/2. So I'm going to do that. And once we do this, we're going to end up, we're going to have that this is equal to the integral of 5 times x to the power 1/2 dx. No problem. I'm going to take the 5 out. So the 5 goes out here. It's a constant. And I have to deal with the integral of x to the power 1/2 dx. But how to deal with this? Let me write it here, the integral of x to the power 1/2 dx. Well, you look at this here, you see, u to the power n, so in our case, n is 1/2. So it will be x to the power 1/2 plus 1 over 1/2 plus 1 plus c. That's what we need to know. Great. So let's look, which x to the power 1/2 plus 1 is 3/2. So you'll see it right here. And again, by just doing some algebra, we will end up with this thing here. So in other words, the antiderivative of so let me write it here. So the antiderivative of 5 square root of x is this guy here, is given by this guy here, by this function here. All right, great. Let's see another example, the fourth one, which is a little bit more complicated. What if you have to compute the integral of this? So the integral of x squared plus the fourth root of x plus 7. So you'll have this on the top, and then on the bottom you have x squared. Wow. All right, great. So what are you going to do? You see, you can divide by x squared. So you can use basic. Let me write it here, some details, because I skipped on purpose some details here. So this guy here. In fact, no, I don't need the integral. I'm just going to do the algebra. So x squared plus the fourth root of x plus 7, everything over x squared. This guy here, if you want to write it, so this is x squared over x squared plus, I don't have enough room, but anyway, plus fourth root of x over x squared plus 7 over x squared. And guess what? You can write this because the fourth root of x is x to the power 1/4 over x squared, so it's x to the 1/4 minus x minus 2, which is 7 over 4, right? Do you get this algebra? This guy here. This guy here is nothing else than just this guy here. Right? And 7 over x squared is nothing else than just 7 times x to the negative 2. All right, great. And now we can integrate each function because we know how to integrate each one of them, right? We can use the sum rule. So here, this integral, let me give you a little bit more detail. So, right. So this is the integral of 1 dx plus the integral. So we can use the sum rule. X to the power negative 7 over 4 dx plus the integral of, well, let me take the constant out. So plus 7 times the integral of x to negative 2 dx. And now we can use the fact that, again, this golden rule, the integral of x to the power n dx is nothing else than just x to the power n plus 1 over n plus 1 plus constant c. So once we use this, right, we can use it for this integral. Also, you can use it for this one here, for both of them. And for the first integral, n is negative 7/4, and for the second integral, n is negative 2. And then, of course, you're going to end up with this. So the integral of 1 dx, whose derivative will give you 1? Well, x. There you go. You have it there. Then the second one, it's this one here. And then the third one with also with the constant 7 will be here. So all that mess combined will give you the antiderivative of the rational function inside, right? Let's see, are there any questions regarding this example? Any questions? So like I said, the only thing you need to do is just the algebra here inside this integral here. This here. Because you'll write it in this way here. Right. Anyway. All right. You'll see, you'll have in your homework plenty of other examples. Some of them are easier, some of them are a little bit more complicated than this. And now I would like to talk about differentiation formulas. And I'd like you to look at these. Look at them. How beautiful they are. Well, probably as you can expect, the antiderivative of sine of u du. So the antiderivative of sine of u is nothing else than just negative cosine of u plus c. Why? Because if you take the derivative of negative cosine of u plus c, you will get sine of u. You understand? Now you can also write the antiderivative of cosine of u du. Well, that it will be sine of u plus c. Because the derivative, if you take the derivative of sine of u plus c, it will give you back the function. Anyway, so the integral of sine of u is negative cosine of u plus c. The integral of cosine of u is sine of u plus c. And then you can also compute the integral of the secant square, cosecant square. So the integral of secant square is tangent plus constant. The integral of cosecant square is negative cotangent plus constant. So, and also, you know, since the derivative of secant of u is secant of u times tangent of u, you can also go back. So you can say that the integral of secant of u times tangent of u du is secant of u plus c, and also the same goes for cosecant of u times cotangent of u du is negative cosecant of u plus c. So these are the anti-differentiation formulas, and for trigonometric functions. So let me just say here. So this is trigonometric functions. But also, maybe you would like to see some more formulas which will involve some other type of trigonometric functions, maybe for the inverse trigonometric functions. Now let's see that. And by the way, let me go back, in fact, to the, this will be very important for you to know. Right? These are very important. You won't have a cheat sheet at Gateway 2 or final exam, so you better know them. All right, great. So like I said, let's see some other formulas which would involve the inverse trigonometric functions. So here we'll deal with inverse trigonometric functions. Well, guess what? Since we know that the derivative of arcsine of u, so when I say arcsine, arctangent, arccosecant, arcsine is sine inverse. So keep that in mind. The same goes for arctan and arcsecant. So arctangent is the inverse of the tangent, and arcsecant is the inverse of the secant. All right, great. So, in other words, the integral of 1 over the square root of 1 minus u squared du is nothing else than just the arcsine of u plus c. Why? Well, if you take the derivative of arcsine of u, and we actually proved this, if I remember correctly, some lectures ago. So the derivative of arcsine of u is nothing else than just 1 over square root of 1 minus u squared. Great. The same thing goes for the arctangent and arcsecant. So the integral of 1 over 1 plus u squared du is the arctangent of u plus c, and the integral of 1 over the absolute value of u times the square root of u squared minus 1 is arcsecant of u plus c. So these are also very important rules that you need to know. For you, I gave you a bunch of rules for you to know. Well, all of them can be proved. I usually hate to tell people to memorize things because I try to avoid as much as I can memorization. But you know, for me to deduce all these rules and to try to prove each and every one of them so that you can, and also it's not productive, it's not convenient for you during the exam. Like, oh my God, what was this rule? It had a minus, has a plus. Okay, let me start deducing it. Maybe I should prove it. So, in fact, I have a funny story to tell you. I was at this very important competition. It's like I don't know, some kind of an international mathematics competition for students, undergraduate students. And I was like, what is the derivative of sine? Is it cosine or negative cosine? I didn't know which one has the negative in front of it. And then I started deducing it to see, I graph it, whatever. And it took me like 20 minutes. So anyway, it can happen. I can tell you that. All right. So these are the, let me go with, so these are the rules here. So this, go back a bit and tell you the first three rules here. As you can see, the first one involving the power function, the second one involving the inverse function, the third one involving the exponential function. Then when we have seen examples, and then we have these rules here involving trigonometric functions, right? And then we have other rules involving, well, rational functions, but also inverse trigonometric functions, right? All right. And now in the remaining time, I would like to do two examples, two applications of integrals. I would like to make use of this notion in with two applications. And the first application I have in mind is the following. Look at this. So let's see, let's call this application 1. So this is the first application. So let's see. The graph of a function f, so capital F, has slope 2x at each point of coordinates x, comma, y, and contains the point 1, 4. And we would like to find the function f. So let's read it together. The graph of the function f has slope 2x at each point, x, y. What is that? Can you translate this to me? Only this. So how you can interpret this? So the graph of a function f has slope 2x at each point. So this means that what? The slope, so at each point, so the slope of the tangent line of each point is what? Do you remember that? Let's see, there is a question here. Not quite. Not quite. So you mean the function f? No, it's not quite linear. But you're close. Well, first, before we go in there, so what is this? We need to remember this. Well, the word I was looking for is called derivative. So remember that the slope of the tangent at each point x, y is given by the derivative, right? right? So what we need to do right now is to find the antiderivative. So finding an antiderivative is like finding the function or drawing the graph given the slope, right? In other words, since the graph of a function f has slope 2x, well, we need to find, so f will be nothing else than just the antiderivative of this. So f of x will be the integral of 2x dx. And we have seen from previous rules that the integrals of 2x dx is nothing else than just x squared plus c, right? And of course, we need to determine that constant c, but there is one piece of information that we haven't used. Also, it contains the 0.14. So in other words, this means what? That f of 1 is 4, right? So if we plug in x equals 1, you will have right? We will have that 1 squared plus c is 4. So in other words, c will be 3. So therefore, we determine the constant c, and our function is nothing else than just this guy here. So it's x squared plus 3. You see, that was the only thing you needed to do. Just remember that the slope of the tangent line at each point is given by the derivative, right? So finding an antiderivative, and also another thing that you need to know is that finding an antiderivative is like finding the function or drawing the graph given the slope. All right, so that's the first application, and then I'd like to do one more. So application number 2. So let's see the second application. You see, it's more like a physics problem, but we have dealt with these kind of problems of a particle moving with acceleration, with velocity. And we have seen that there is a relationship between these in terms of derivatives. So guess what? It will always be a relationship between them in terms of the antiderivative, right? So what do we have? So a particle moves with acceleration a of t, -32 for t greater than 0. If the particle is at position s equals 5 and has velocity v equals -2 at t equals 1, then we're wondering, where is it at t equals 4? So in other words, look here. So I know the acceleration. And you know, I'm wondering about the velocity, about position, about velocity. So I know the position at s equals 5. I know the velocity of v equals 2. Then I'm wondering what is the position at t equals 4. So when I'm asking where is the particle, so I'm wondering what is the position at t equals 4. In other words, what is the position at t equals 4? That is the question I'm asking. All right, great. So is there a way for me to relate the velocity and the acceleration in terms of the antiderivative? So first, what is the relationship between the velocity and the acceleration? Can you tell me? What did we say? That the velocity, the derivative of the velocity is nothing else than the acceleration, right? Remember? And also the velocity is nothing else than just the derivative of the position. That's what we knew so far. So now I know the acceleration. Maybe I should find out the velocity. Well, no problem. I can do that. Look at this here. Since the the derivative of the velocity is the acceleration, then the antiderivative of the acceleration is nothing else than just the velocity, right? All right, great. So we can write this as v of t is the integral of a of t dt, but I know that a of t is negative 32. So the integral of negative 32 dt, I'm just going to take out negative 32. So it's nothing else than just the integral of 1 dt, which is t. So the velocity is negative 32t plus c1 plus a constant c1. Maybe I should determine c1 because I know something happens with the velocity. You see, I know the velocity function for t greater than 0, but I also know, if you look at this, I have this piece of information that the velocity is negative 2 at t equals 1. So v of 1 is negative 2. So we know that. So let's write that. V of 1 is negative 2. So let's translate this. So I know that v of 1 is negative 2, but v of 1 is also negative 32 plus c1. So I can find c1, and c1 will be 30. And therefore, my velocity function will be negative 32t plus 30. Great. But we're not done because I'm interested in what is the position of at t equals 4. So I know the velocity function. Now I need to find what? Can you tell me? Given the velocity of a particle, what can I do? I can find the position, right? And how do I find the position of the particle? S of t. By integrating the velocity. So let's do that. So the position S of t is nothing else than just the integral of v of t dt. Well, I know that v of t is negative 32t plus 30. We're going to integrate that. And once we integrate that, you're going to end up with this. And I'm going to leave these details to you as an exercise, because we're going to use the properties of the integrals here. And we're going to end up with this function here with negative 16t squared plus 30t plus c2. Well, beautiful. The only thing I need to deal with is the constant c2. But there is another piece of information that I know, which says the following. The particle is at the position s equals 5. So I know that when at t equals 1. So I know that s of 1 is 5, right? So let's write this here. S of 1 is 5. So s of 1 is 5. So this means that it just replaced by, you replace t by 1. So this will give you that s of 1 is negative 16 plus 30 plus c2 equals 5. And then you'll find out c2, and then, which is negative 9, you can write the position function. So here, we wrote the velocity function, right here. See, by just integrating, and here we found the position function by integrating the velocity. Great, but look, I'm not done yet. I'm interested what happens at t equals 4. So what is the position at t equals 4? In other words, we need to evaluate s of 4, and this is just simple algebra, which I'll leave it to you. We just replace t by 4, and anyway, it will give you negative 145. So this is the position of the particle at the time t equals 4. right? You see, the moral of this problem is the following. Since the velocity is the derivative of the position and the acceleration is the derivative of the velocity, I can go back and I can say that the antiderivative of the acceleration is the velocity, and also the antiderivative of the velocity is the position. So I can go back, right? Any questions about this problem? Anyway, you look you have plenty of time to look at it again once I send you the video. All right, I think I'm going to stop here for today. So guys, this is just the warm-up for this chapter. So there are plenty of interesting things coming out. Also, I think I forgot to mention, but another important thing is that we haven't used, I haven't said it, but it's kind of in disguise, is what we call the fundamental theorem of calculus, which will be discussed next time, or yeah, next week for sure. All right, feel free to stop by my office hours in like 10 minutes. If you have any questions about whatever, about math, life in general, just let me know. All right, I'll see you. Take care. Bye-bye.